Welcome to the course on advanced power electronics. So we'll cover in this lecture zero current switching converters. So coming to this zero current switching converter with quasi-resonant converters, this is the basic concept of switch configuration of zero voltage current switching converter. So here the switches of zero current switching resonant converter turn on and turn off at zero current. And if in the above circuit, if L is connected in series with the power switch S1 to achieve ZVS, and capacitance is connected with the shunt, so we call it L type of resonant switch. And if the capacitance is connected in parallel with inductor and switch, then we call it M type resonant zero current switching switch. So in both type, the inductor limits the di by dt of the switch current, and L and C constitute a series resonant circuit. And when the switch current is zero, there is a current I equal to C dV by dt flowing through the internal capacitance Cj due to the finite slope of the switch voltage at turn off, and the current flowing through causes power dissipation in the switch and limits the high switching frequency. So you can just see here how the half wave ZVS, resonant switch. Here you can see, of course, that the same concept, that the capacitor connected in parallel to, in really at the output or after the inductor, or the capacitance connected when the switch, inductor and diodes are connected in series and capacitance across it. So in this type of configuration, the current flows in unidirectional due to the presence of diode, and D1 is in series with the switch. And in full wave, you can just see here the diode in parallel with the switch, and then inductor and capacitor. And in second case, of course, capacitor is connected after the parallel to the even cracking inductor in series. So in this type configuration, the current flows in bidirectional as the D1 is connected in anti-parallel to the switch. So here coming to that ZVS switching cell, as we see in the circuit, we call it the input and output, and where ZVS switch. And what is this? Typically, your PWM switch is typically consisting of your switch and diode, like typically in case of buck converter. So the above figure illustrates a generic buck converter consisting of switch cell cascaded by LC low pass filter. And when the switch cell is realized as a adjoining figure is shown on the right side, then the conventional buck boost conventional PWM converter is obtained. So there are two types of possible realization of switching cell, of zero current switching cell: the half wave zero current switching quasi-resonant switch, and the full wave zero current switching quasi-resonant switch. So in this switch cell, the resonant circuit, resonant tank capacitor CR is placed in parallel with diode, while the resonant tank LR is in place in series with the above active transistor element. So both resonant switch cells require a two-coordinate single pole, single throw switch, and in either switch cell, the LR and CR elements, the resonating elements, are relatively small in value, such that their resonant frequency F0 is greater than the switching frequency Fs, where F0 equal to 1 upon 2 pi under root LR CR, or omega 0 upon 2 pi. And this is the typically, you can say, the half wave ZVS quasi-resonant circuit, where the inductor and diodes are connected in series, of course, of the switch line. So in half wave switch, the switch cell shown above, the diode D1 is in series with the transistor Q1, as you see above, and current this causes the Q1 and D1 ST switch to turn on and turn off at the first zero crossing of the tank inductor current I1T. And in case of full wave, you can just see here the full wave zero current switching resonant converter. So in full wave switch cell shown above, anti-parallel diode D1 allow the bidirectional flow of the tank inductor current I1. And with this switch network, the Q1 minus D1, this ST switch is normally turned off, and the second crossing of the I1 waveform. So coming to L type zero current switching resonant converters, where capacitance is connected after the inductor. So you can see the circuit after the switch, inductor, series inductor is there, then the capacitor, and then of course in this buck converter we have a filling diode followed by LC filter line. So a L-type series resonant converter is shown in the above figure, and the circuit operation can be divided into 5 modes. So we shall redefine the time origin t equal to 0 at the beginning of each mode. So coming to mode 1, this mode is valid from time varying 0 to t1, as you can see here, where switch H1 is turned on and diode Tm conducts, and the inductor current IL, which rises linearly, is given by IL equal to Vs upon L into T, and this mode stands at T equal to T1 when IL equal to T equal to T1 equal to I0, and that is why T1 equal to I0 L upon Vs. Now coming to mode 2, this mode valid from 0 to time equal to 0 to T1, and switch S1 remains on, and but diode Dm is off, and the inductor current IL is given by IL equal to Im sin omega 0 t plus I0, where Im equal to Vs under root C upon L, and omega 0 is 1 upon 1 divided by under root LC. So this capacitor voltage Vc given by Vc equal to Vs in bracket 1 minus cos omega 0 t. So the peak switch current which occurs at t equal to pi by 2 under root LC, so Ip equal to Im plus I0, and capacitor peak voltage is Vc peak equal to 2 Vs. So this mode ends at t equal to T2 and IL equal to T equal to I0, and Vc equal to T equal to Vc2 equal to 2 Vs. Therefore T2 equal to pi under root LC. Coming to mode 3, the mode 3 is valid from 0 to T3, and this inductor current that falls from I0 to 0 is given as IL equal to I0 minus Im sin omega 0 t, and the capacitor voltage is given by Vc equal to 2 Vs0 cos omega 0 t, and this mode ends at t equal to T3 when IL equal to 0 and Vc equal to Vc3, and then T3 equal to under root LC sin inverse 1 upon x, where x is Im upon I0, that is equal to Vs upon I0 under root C upon L. Now going to mode 4, this mode is valid for 0 to time 0 to T4, and the capacitor supply the load current I0, and its voltage is given by Vc equal to Vc3 minus I0 upon C into T, and this mode ends and time equal to T equal to 4 when Vc equal to 0 and the T4 equal to Vc3 C upon I0. Now coming to mode 5, this mode valid from 0 to T5, and when the capacitor voltage time to be negative, the diode Dm conduct, and the load current I0 flows through the diode Dm. This mode ends at T equal to T5 when the switch S1 is turned on again, and the cycle is repeated till T5 equal to T minus in bracket T1 plus T2 plus T3 plus T4. And these are the typical waveform you can see for inductor current and the capacitor voltage. I mean for all for mode T1, T2, T3, T4, T5, which we already defined earlier, and the waveform for IL, VSC for the L type of ZVS resonant converter are shown in the above figure. So the peak switch voltage equal to the DC supply voltage Vs, and because the switch current is 0 and the turn on and turn off, the switching loss, which is product of V and I, becomes very small. The peak resonant current Im must be higher than the load current I0, and this sets limit on the minimum value of load resistance R. However, by placing an anti-parallel diode across the switch, the output voltage can be made insensitive to the load variation. Now coming to M-type ZCS resonant converter. So I mean you can just see how the typically capacitor now in case of M-type capacitor connected in parallel with the device and switch inductor. That makes it M-type of resonant converter, followed by the of course filling diode and LC filter of the back converter. So an M-type ZVS resonant converter is shown in the above figure, and the circuit operation can be divided into again 5 modes. When we'll define the time origin t equal to 0 and at the beginning of each mode, and then coming to the first mode when analysis is made exactly similar to mode 1 of L-type ZVS where the switch is on, and mode 2 the mode valid 0 to T2 and capacitor voltage Vc equal to Vs cos omega t. As you can see in the circuit, the peak capacitor voltage equal to Vs. At the end of this mode t equal to T2, so Vc equal to Vc2 equal to minus Vs. Now coming to mode 3, this mode is valid from t equal to 0 to T3, and the capacitor voltage is given as Vc equal to minus Vs cos omega 0 t. At the end of this mode at t equal to T3, Vc equal to Vc3 And it should be noted that VC3 can have a negative value, and this is an important parameter while selecting the type of capacitor to be used in the circuit. And in case of mode 4, you can see when switch is open, the mode and T equal to T4 and Vc equal to Vs, and thus T4 equal to Vs minus V3 C divided by I0. And mode 5, the analysis is similar to mode 5 of L type of ZVS, as you can see the capacitor in parallel with. And these are the typical waveform for all inductor current and capacitor voltage waveform for all 5 modes starting T1, T2, T3, T4 and T5. Now coming to ZCS quasi-resonant buck converter. So this is typically the circuit. You can see here the capacitance is connected in parallel, resonant capacitor, inductor connected in series, and with that series diode with the switch. The quasi-resonant buck converter is shown in above figure, and it is formed by replacing the power switch in conventional pendulum buck converter with ZC zero current resonant switch. And coming to the output in, this LF is sufficiently large so that the output current is approximately constant, that is shown as a current source, and this leads to simplification of circuit by combining the load and the output inductor and the capacitor combination to be a current source as shown in the above figure. And coming to mode 1 from 0 to T1, as you can see switch is on. So in this mode, the operation of the switch is turned on by supplying a gate pulse to it, and the load current is supplied by IS and ID, and the voltage across CR is 0 as the diode is in its conducting state, and the load current is given I0 equal to IS minus ID, and the voltage across the switch is VDC equal to L DIL upon dt, and hence the inductor current can be calculated IL equal to, you are in integral VDC d upon L into dt, that is ILT, or IL equal to VDC T upon L. So the inductor current rises linearly with respect to time. At time T1, the load current is supplied only by using switch current, which is identical to the inductor current. And at T equal to T1, I0 equal to IL, and that is I0 equal to VDC to T1 upon L. The time at which the inductor current IL equals to the load current I0 is T1 equal to I0 L upon VDC. After the time T1, the inductor current and capacitor voltage are as I0 equal to IL and Vc equal to 0. Now coming to mode 2, that is T1 varying from T1 to T2 when the switch is closed and the diode is open. So in this mode, the load current is supplied by the inductor current, and as the diode is in off state, the resonant capacitor comes into picture. So supply voltage VDC equal to L DIL upon dt plus Vc, and differentiating this, we get 0 equal to L d square upon d square IL upon dt square plus dVc upon dt, and IC equal to, the capacitor current is IC equal to IL minus I0, or IL minus I0 equal to C dVc by dt, hence dL d square L IL upon dt square plus IL upon C minus I0 upon C equal to 0. So applying Laplace, the initial condition IL 0 equal to I0 and IL dash equal to VDC upon L. So in bracket S square ILS minus S IL 0 plus IL upon LC minus I dash L equal to I0 as SLC, and that makes ILS in bracket S square plus 1 upon LC equal to VDC upon L plus I0 plus SI0 plus I0 SLC, taking omega 0 square 1 upon LC, that is ILS in bracket S square plus I omega square equal to VDC upon L plus SI0 plus I0 SLC. So solving IL for and putting characteristic impedance Z0 equal to omega 0 L, and that is ILT equal to VDC upon 0 sin omega 0 t plus I0, and capacitor voltage found IL minus I0 equal to VDC upon Z0 sin omega 0 t equal to C dVc by dt, or equal to Vc t equal to integral VDC upon Z0 into C sin omega 0 t into dt, or Vc equal to or minus VDC divided by Z0 omega 0 C into cos omega 0 t plus K. So at Z0 omega 0 C equal to 1, so Vc comes minus VDC cos omega 0 t plus K. At t equal to 0, Vc equal to 0, so K becomes VDC and Vc becomes VDC in bracket 1 minus cos omega 0 t. So at t equal to 2, inductor current is IL equal to 0. Therefore, we design L and CR such that the inductor current IL, that is switch current, is 0 before the gate pulse becomes 0, and the time at which the inductor current becomes 0. So T2 equal to 1 upon 0 in bracket phi plus sine inverse Z0 I0 upon BDC, I mean plus I0 L upon BDC. Now coming to mode 3, when your switch and diode both are off. In this mode, the switch is in the off state and the equivalent circuit is on there. The load current is supplied by IC as shown the charge left on the capacitor. So the load current is C equal to dVc by dt equal to minus I0, and the capacitor voltage is V0 equal to integral I0 upon C dt, or Vc equal to minus I0 upon C in bracket T minus T2 plus K, and at T equal to T2, Vc equal to VDC in bracket 1 minus cos omega 0 T, or K equal to VDC in bracket 1 minus cos omega T2 minus T1, and Vc is equal to minus I0 upon C in bracket T minus T2 plus VDC in bracket 1 minus cos omega 0 T2 minus T1. Coming to mode 4, when switch is off, and typically in this mode the switch is in the off condition and the load current supplied by the diode alone, and the capacitor voltage is 0. The load current is ID equal to I0, and this mode is known as freewheeling mode, as the load current freewheels through the diode. And these are the typical waveform for all the modes like T1, T2 and T3. And here the important parameter for this Cauchy resonant converter is voltage conversion ratio M equal to V0 upon Vi, and characteristic impedance ZR equal to under root LR upon CR, and resonant frequency FR equal to 1 upon 2 pi under root LR CR, and normalized load resistance R equal to RL upon ZR, and normalized switching frequency equal to lambda equal to Fs upon Fr. And these are typically the characteristic between M and gamma, between the conversion ratio M and normalized frequency gamma for different values of normalized load resistance R. So the voltage conversion ratio M is sensitive to the load variation. At light load conditions, the unused energy is stored in CR, leading to an increase in the output voltage. Thus, the switching frequency had to be controlled to regulate the output voltage. If an anti-parallel diode is connected across the switch, the converter will be operating in the full wave mode, and the operation becomes similar to half wave mode. However, the inductor current is allowed to reverse through the anti-parallel diode, and the duration for the resonant stage is lengthened. And this permits excess energy in the resonant circuit at light loads to be transferred back to the voltage source Vi, and this significantly reduces the dependence on V0 on the output load. So ZCS converters can eliminate the switching losses at turn off and reduce the switching losses at turn on. And because a relatively large capacitor is connected across the diode DM, the converter operation becomes insensitive to the diode junction capacitance. And when power MOSFET are used for ZCS, the energy stored in the device capacitance is dissipated during turn on. So this capacitance turn on loss is proportional to the switching frequency. So during turn on, the high rate of change of voltage may appear in the gate drive circuit due to coupling through the Miller capacitor, thus increasing the switching loss and noise. So another limitation is the switches are under a high current stress, resulting in a high conduction loss. However, ZCS is particularly effective in reducing switching loss for power devices such as IGBT with large tail current in the turn-off process. But the nature of resonant tank and the ZCS, the peak current is much higher than in a square wave. So in addition, high voltage becomes established across the switch in the off state after the resonant oscillation, and when the switch is turned on again, the energy stored in the output capacitor becomes discharged through the switch, causing a significant power loss at high frequency and high voltage, and this switching loss can be reduced by using the ZVS. So ZVS eliminates the capacitor turn-on loss. It is suitable for high frequency operation, and without any voltage clamping, the switches may be subjected to excessive voltage stress, which is proportional to load. For both ZCS and ZVS, the output voltage can be achieved by varying the frequency, and the ZCS operates with a constant on-time control, where ZVS with constant off-time control. And coming to Cauchy resonant controller IC, so need for Cauchy resonant controller IC. The Cauchy resonant controller IC simplifies the design of high-frequency flyback converter by integrating critical control and protection features into single chip. And compared to designing the converter from scratch, they reduce the design complexity, development time, and BOM cost while ensuring reliable operation. And the QR controller, Cauchy resonant controller, optimize the switching time to minimize losses, making them ideal for application demanding energy efficiency and EMI compliance. So coming to typically composition of quasi resonant controller IC. So it's an integrated PWM controller for quasi resonant operation and built-in feedback control for output voltage current regulation. Now protection circuit typically for over voltage overcurrent short circuit, thermal shutdown and breakdown detection, and startup circuit for enabling operation directly from high voltage input bus. And some IC also contain a built-in power MOSFET eliminating the need for external switch. So other components of the resonant converter like inductor, high frequency transformer, output rectifier diode, sensing and feedback circuitry, filter capacitors, current limiting resistor and other auxiliary components can be connected externally as per the design and application. And QR controllers are widely used in low to medium power flyback converters for switch mode power applications like adapters, TV and LED drivers. And examples are ICE2QR 4765 of Infineon and QCC 28780 of Texas Instruments. And this is typically the chip details of this of manufacture of Infineon of ICE2Q R475, and the SKU the detail are given here. How the key features are quasi-resonant operation of high frequency and low electromagnetic interference, and that integrated burst mode for ultra low standby supply of less than 100 milliwatt, and built-in protection with all voltage over current of brownout and thermal shutdown, and simplified design with the minimal external component. And application ideal for flyback converter in switch mode power supply for adapter charger for industrial power supply. And this is typically internal detail of the total circuit, how it really work here with the input supply with the rectifier, then the capacitor, and then the typically this flyback converter of the output, typically the regulator with the isolation and all. The above figure shows the block diagram of Infineon IC2QR4765, and the PWM converter and MOSFET are the part of package, while the input rectifier, transformer, number, reference, feedback, voltage, etc. are connected externally as you can in the circuit. And this is another quasi-resonant control IC form of UCC of Texas Instruments, and key features are advanced QR flyback controller with hybrid switching modes of QR plus adaptive value switching, and high power density support with wide input-output voltage range, and extremely low standby power less than 10 milliwatt with active mode efficiency of greater than 90%. And applications are designed for compact high efficiency consumer power supply in consumer electronics, telecom, and industrial power supply. And this is the total circuit of this. So the block diagram of it, typically of your UCC Texas 28780 with the chip as well as the control and complete set of supply. So both ICE2Q4R4765 and UCC 28780 are used mostly for QR flyback converter, quasi-resonant flyback converter for the advantage of valley switching. And valley switching is a technique used in the quasi-resonant converter where the power MOSFET is turned on, and when the drain source voltage reaches its maximum valley point during the resonant oscillation of the circuit, and this minimizes the switching losses and electromagnetic interference, improving the overall efficiency. And this type of switching has the following advantage: the reduced switching losses by turning on the MOSFET at the lowest drain source voltage, and improved EMI performance. The quasi-resonant operation reduces high frequency noise, and typically high efficiency essential for modern energy standards. Now coming to numerical examples, is example 1, AL type zero current switching resonant converter delivers a maximum power of PL equal to 400 milliwatt at V equal to 4 volt. The supply voltage is Vs equal to 12 volt. Maximum operating frequency is F max equal to 50 kilowatt. Determine the value of LNC. Assume that the interval T1 and T3 are small and X equal to IM upon I0 equal to 1.5. So given that, so for solution, given that Vs equal to 12 volt, F equal to F max equal to 50 kilowatt, and T equal to 1 upon 50 kilowatts equal to 20 microsecond, and PL equal to V0, I0 equal to 400 milli, which gives the I0 equal to 100 milliampere. And now the time interval various modes of operation are as T1 equal to I0 L upon Vs, and T2 equal to pi under root LC, T3 equal to under root LC sin inverse 1 upon X, and T4 equal to Vc3 C upon I0, and T5 equal to T minus in bracket T1, T2, T3 plus T4. For maximum frequency, the prevailing time of the diode, that is T5, has to be 0. So moreover, it is given that T1 equal to T3 equal to 0, and hence so T equal to T2 plus T4, that is pi under root LC plus Vc3C upon I0. So for the peak voltage, capacitor voltage Vc3 equal to 2 Vs, that is X equal to Vs upon I0 under root CL, So we get here from putting value C equal to 0. Taking C0 equal to 0.407 microwatt and Lx comes equal to 260.52 microhenry. Coming to example 2, a Z0 current switching resonant converter used in a smartphone charger delivers a maximum power of PL equal to 500 milliwatt at V0 equal to 5 volt. The supply voltage is PS equal to 15 volt and the maximum operating frequency is F max equal to 40 kilohertz. Assume X equal to IM upon I0 equal to 2 and T1 equal to T3 equal to 0. Calculate the value of stand C. So given for solution given here, PS equal to 15 volt, F equal to F max 40 kilohertz and T equal to 1 upon X 25 microsecond and PL equal to V0 I0 that is 500 milliwatt and V0 is 5 volt. So from here we get I0 equal to 100 milliampere and time interval are given T equal to T2 plus T4 and equal to pi under root LCD plus V3 upon C upon I0 where V3 is equal to 2 Vs and X equal to V0 upon I0 under root CL. So rewriting pi VSC upon X I0 plus 2 Vs upon I0 into C equal to T and solving for C equal to T upon pi Vs upon X I0 plus 2 Vs upon I0 equal to 0.0334 microfarad and expression of inductor L equal to Vs upon X I0 equals square C. So from which we get the putting value C L equal to 375.6 microhenry. Coming to example 3, a zero current switching resonant converter used in a battery charger operates with a supply voltage of Vs equal to 20 volt and output voltage of V0 equal to 10 volt. The load power is PL equal to 1 watt and the maximum operating frequency is F max equal to 40 kilohertz and assume X equal to 1.6 and time interval T equal to T1 equal to 1 microsecond, T3 equal to 0.5 microsecond. Calculate the inductor, capacitor and the switching period. So given that Vs equal to 20 volt for solution, V0 equal to 10 volt, PL equal to 1 watt, F max 40 kilohertz, X equal to 1.6, T1 equal to 1 microsecond, T3 0.5 microsecond. So calculate I0, PL equal to V0 I0 from which we get I0 equal to 0.1 ampere and the switching period T can be calculated from the switching frequency. So T equal to 1 upon F max, so that is equal to 25 microsecond and time total T equal to T1 plus T2 plus T3 plus T4 where the T1 is I0 L0 upon Vs, that is T2 equal to pi under root LC, T3 equal to under root LC sin inverse 1 upon X where T4 equal to Vc3 Vc upon I0 and Vc3 equal to 2 Vs. So T2 plus T4 equal to T minus T1 minus T3 that is 25 microsecond minus 1 minus 0.5 that is 23.5 microfarad. As substituting this T2 equal to pi under root LC, so T4 is Vc3 C upon I0. So from where putting all these value we get the C equal to 0.0463 microfarad and L equal to putting value in Vs upon X0 square C that is comes 363.4 microhenry. Coming to example 4, a zero current switching resonant buck converter operates LR equal to 200 microhenry and CR equal to 0.025 microfarad. The supply voltage Vs equal to 24 volt and output voltage V0 equal to 5 volt and the load power is PL equal to 1 watt. To obtain the expression for the inductor current when it flows through the resonant tank. The resonant frequency of the tank circuit is omega 0 equal to 1 upon under root LRCR. Putting value it comes typically your 0.44723 447.2136 kilo radian per second and the average load current obtained I0 equal to PL upon V0 that's 0.2 ampere and characteristic impedance ZR equal to under LR upon CR that is 89.44 and the inductor current IL equal to Vs upon ZR sin omega 0 t plus I0. So it comes IL equal to 0.268 sin 47 to 213.6 t plus 0.2. Coming to example 5, a zero current switching resonant converter operates L equal to 50 microhenry and C equal to 0.035 microfarad. The supply voltage Vs equal to 24 volt and the load power is PL equal to 0.5 watt, 5 max equal to 30 kilohertz and X equal to 1.8. Calculate the time interval T1, T2, T3, T4 and the peak voltage across the capacitor Vc3. So for solution given here L equal to 50 microhenry, C equal to 0.035 microfarad, Vs equal to 24 volt, PL equal to 0.5, F max 30 kilohertz, X equal to 0.18. So calculate I0 equal to from power, we get the PL upon V0, that comes 0.02083 ampere, and the switching period T1 upon Fmax, that comes 33.33 microsecond, and T2 is pi under root LC, it comes putting value 9.33 microsecond, and T3 comes under root LC and sine inverse 1 upon X. So this T3 comes 1.53 microsecond, and VC3 is 2 Vs, that is 48 volt, and T4 is equal to VC3C upon I0. So putting value, it comes 8.06 microsecond, and time interval T1 equal to T minus T2 minus T3 T4. So T1 comes 44.42 microsecond. Coming to example 6, a zero current switching resonant converter operates at Fmax equal to 60 kW, L equal to 300 microhenry, and C equal to 0.025 microfarad. The supply voltage Vs equal to 18 volt and X equal to 1.4. And if T1 takes 2 microseconds, calculate I0, T2, T3, T4, and T. So solution is given Fmax equal to 60 kilohertz, L equal to 300 microhenry, C equal to 0.025 microfarad, Vs equal to 18 volt, T1 equal to 2 microsecond, X equal to 1.4. So switching time interval T equal to 1 upon Fmax equal to 16.67 microsecond, and T2 is pi under root LC. So putting value, it comes 8.63 microhenry, and T3 equal to under root LC sine inverse 1 upon X. So putting value, it comes T3 2.04 microsecond, and T4 T minus T1 minus T2 minus T3, that comes 4 microsecond, and T4 comes V3 upon VC3 C upon I0. So and VC3 putting equal to Vs, so I0, VC3 upon C upon T4, so it comes 0.225 ampere. So coming to example 7, a zero current switching resonant converter have L equal to 200 microhenry, C equal to 0.02 microfarad, and X equal to 1.2. The load current is I0 equal to 0.15 ampere, and Fmax equal to 70 kilowatt. Calculate the time interval T1, T2, T3, T4, and T, and also find Vs if VC3 equal to Vs. So given here L equal to, for solution, L equal to 200 microhenry, C equal to 0.02 microfarad, X equal to 1.2, I0 equal to 0.15, and Fmax equal to 70 kilowatt. So switching period is T equal to 1 upon Fmax, and putting value, it comes 14.29 microsecond, and T2 is pi under root LC, putting value, it comes 6.28 microsecond, and T3 under root LC sine inverse 1 upon X. So putting value, it comes T3 comes 1.31 microsecond, and T4 is T minus T1 minus T2 minus T4. So T3, it comes 6.7 microsecond, and VC3 equal to Vs, that is T4 here TVC3 upon Ig. So Vs comes here 25.125 volt. Coming to example 8, an L-type Cauchy resonant zero switching current switching converter has a resonant circuit parameter as L equal to 300 microhenry, equal to 1 microfarad. The output voltage is 10 volt, and the load resistance is 10 ohm. The source voltage is 24 volt. Calculate the time required for resonant inductor current to reach the value of average load current when the switch is turned on. So the solution is the average load current is calculated I0 equal to V0 upon R, that comes 1 ampere, and when the switch is turned on, the inductor current rises almost linearly till it reaches the average value of the load current. So hence the Vs equal to I0 L I0 upon delta T. So delta T comes putting value 12.5 microsecond, and hence the time required for the resonant inductor current to reach the value of average load current when the switch is turned on is 12.5 microsecond. So coming to example 9, a Cauchy resonant buck converter is supplied using a 48 volt DC source. The output voltage is 12 volt while delivering load power of 5 watt. Assume the filter inductance to be large enough for the load current to be constant, and resonant tank circuit parameter LR equal to 100 microhenry, CR equal to 1 microfarad. Determine the minimum width of the gate pulse required to ensure ZCS for switch. And for solution, the average load current is I0 PL upon V0, that comes 0.417 ampere, and the resonant frequency omega 0 equal to 1 upon LRCR, that comes 100 into 10 power 3 radian per second, and the characteristic impedance is ZR equal to under root LR upon CR, that comes 10 ohm, and the time taken for current to reach 0, T equal to 1 upon omega G in bracket pi times sine inverse ZR I0 VDC in bracket close plus I0 L upon VDC. So putting the value and solving it, T comes 33.3 microsecond. Hence the width of the gate pulse should be greater than 33.2 microsecond for successful zero current switching. Coming to example 10, In the previous example, calculate the following parameter: resonant frequency, normalized load resistance, normalized switching frequency, assume a suitable switching frequency for the calculation. The solution is, since the minimum pulse width required 33.2 microseconds, the on time period is to be chosen greater than this value. So considering on time period 50 microseconds and same off time, the total period occurs 100 microseconds. The switching frequency is R1 upon Ts, that is 10 kilohertz. And resonant frequency of R equal to omega R upon 2 pi. So putting value would come 15.92 kilohertz, and normalized load resistance R equal to RL upon ZR. So it comes, putting value 0.2083, and normalized switching frequency lambda equal to Fs upon Fr. Putting value would come 0.628. And these are the references for which this material is prepared. And thank you.